My name is Flash Isaac, and I'm a teacher from the future. When I was much younger, I saw thousands and thousands of people fail Jamb and unable to gain admission. This made me travel in time. Now I am back with the Flashlearners Jamb app and a series on YouTube tagged 120 Days to Jamb. My mission is to help you blast Jamb and as well get justice for everyone who Jamb has served breakfast. Hello, this is episode number 35 of the 120 Days to Jamb Chemistry with Flash Isaac. In this episode, we shall be looking at energy changes, that is, spontaneity of chemical reactions. A chemical reaction is said to be spontaneous if it proceeds under the given set of conditions. A reaction is said to be spontaneous if it proceeds or it occurs under the given conditions without external factors, without external help, without interference. There are three factors that determine the spontaneity of chemical reactions. In other words, there are three factors that determine whether a reaction will proceed or not. The factors are enthalpy, entropy, and Gibbs free energy. Enthalpy, represented by H, is the energy content, the heat content of a reaction. The heat the reaction possesses. Some reaction gives out heat, some reaction require heat. For example, burning of candle gives out heat to the environment, while an ice that is melting requires heat from the environment to be able to melt, to be able to change from that solid state to liquid state. In both cases, you see that there is the presence of heat. So the heat content of a reaction is enthalpy. But there is something we are interested in, not the enthalpy, but the enthalpy change, delta H, because we are dealing with energy changes. Delta H is enthalpy change and is the energy change that occurs or accompanies a chemical reaction. Now look at this. Enthalpy itself is the heat content of the reaction, but enthalpy change is the change in heat content. In reactions, you have the reactant part and the product part. If acids or an acid react with base to form salt and water, acid and bases are the reactants, salt and water the product. So the heat change delta H is simply the heat of the product minus the heat of the reactant. You check the reactant, what is the heat content of this reactant? You check the product, what is the heat content of this product? Which means if the product is hotter than the reactant, the enthalpy change will be positive. If the reactants were hot after the products are formed, the products are now cooler, it simply means that the heat of reactant is higher than the heat of product and the enthalpy change will be negative. The second factor that determines the spontaneity of chemical reaction is entropy. Entropy is the degree of disorderliness of a chemical system. Entropy is the degree of randomness, degree of scatterness, degree of zagazaganess, degree of craziness, degree of scatterness of a chemical system. That is entropy. But we are more interested in entropy change since we are dealing with energy changes. Now, entropy change is delta S. Entropy change is the entropy of the product minus the entropy of the reactant. So, how disorderly is the product? How disorderly is the reactant? That means gases will have higher entropy than liquid and solid because gases, they have degree of randomness, zagazaganess, and anyhowness. That is entropy for you. Then we have Gibbs free energy. Gibbs free energy. The Gibbs free energy is the energy available for doing work. Now, what is work in this case? Work in this case refers to reactant changing to product. In fact, for reactant to change to product, work is done. Look at this. These are reactants. It has to go through this stage down to form product. Even here, you see reactant has to hustle, climb to meet certain factors to get to product. So work is done. And Gibbs free energy or energy change is delta G. All that being said, if these guys are the factors that determine spontaneity of chemical reaction, what value of these guys will make reaction spontaneous or not spontaneous? Before then, let's look at something. In terms of heat change, or in terms of heat changes, or in terms of enthalpy, a reaction can be exothermic or endothermic. Exothermic or endothermic. An endothermic reaction is a reaction that needs heat to proceed. It needs heat from the environment to proceed. Like I stated earlier, melting of ice. Ice needs heat from the surrounding to melt. Now, exothermic reaction, exo, are reactions that gives out heat to the environment. As the reaction is taking place, heat is given out. Let's take a look at burning of candle, like I said earlier. As candle is burning, you notice that the environment gets hotter. The environment gets hotter. It is giving out heat. Now, a situation where you are carrying out a reaction in this basin, and this reaction is giving out heat. What do you think will happen? The reactive vessel will get hotter, so hot, because heat is given off. Now, what if this reaction requires heat from the environment? You notice that it will be absorbing all the heat possible. The reactive vessel will get so cooler. Exothermic reaction. In exothermic reaction, delta H is negative. Why? The heat of the reactant or the reaction is more than the heat of the product, because the reaction or the reactant are so hot that they are giving it out. So the product gets hotter. Therefore, delta H will be negative. For endothermic reaction, since they are absorbing heat, the reactants absorb heat. As the products are being formed, the product gets hotter. So the heat of the product is more than the heat of the reactant. Therefore, delta H is positive. I've said about 3 things now. 1, for endothermic reaction, they need heat to proceed. They take heat from the environment. For endothermic reaction, again, the delta H is positive. For endothermic reaction, again, the reactive vessel gets cooler. I've said 3 things about exothermic reaction. Exothermic reaction, they give out heat to the surrounding. Since the product gets hotter, the reactant gives out heat, product gets hotter, delta H is negative because the heat of the reactants are more than the heat of the product. And since it gives out heat, in exothermic reaction, the reactive vessel will get hotter. Now, if entropy is the degree of the solidness of a system, what do you think will happen for a reaction that is constantly releasing heat to the environment? Which means the entropy of the environment will be higher for exothermic reaction, since it is giving out heat burning the environment. Now, let's see other examples of exo and endothermic reaction. Anytime you hear burning, there is high chance that it is exothermic reaction, because burning will give out heat to the environment. Anytime you hear evaporation, endothermic reaction should come to your mind. Why? For water vapor to evaporate, they need heat. So heat is required for evaporation. As they get heat, they become gases and they begin to evaporate. Anytime you hear condensation, exothermic reaction should come to your mind, because when water vapor or gases get so hot, they give out the heat. Take. As they donate the heat, they change from gases to liquids. They've evaporated. Now, more examples of endothermic reaction are formation of nitric oxide. Generally, heat of formation is exothermic. When things are formed, when there is formation, it is likely going to be exothermic reaction. But for the formation of nitric oxide, nitrogen reacting with oxygen, oxygen have double bond. So the two atoms of oxygen or one molecule of oxygen with double bond forms a very strong bond that will be difficult to break. So for that bond to break and for nitrogen to combine with oxygen to form nitric oxide, heat is required from the environment. So it absorbs heat. Dissolution of ammonium chloride in water is endothermic. Heat is required. The reactive vessel gets cooler. Dissolution of salt in water generally are endothermic. Photosynthesis is an endothermic reaction. Now, let's look at exothermic reaction. Burning of coal is exothermic. As you can see, delta H is negative. Now, for formation of nitric oxide, delta H is plus 180 kilojoule. That is positive. Anytime in a reaction you see delta H negative, it shows that it is exothermic and heat is given off. Anytime in a reaction you see delta H positive, it shows that it is endothermic and heat is absorbed. Now, formation of ammonia is exothermic. Burning of natural gas, methane, in oxygen is exothermic. We form carbon dioxide and water. This is the heat of the product. This is the heat of the reactant. What do you notice? In endothermic reaction, the heat of the product is higher than the heat of the reactant. Now look at exothermic reaction. Here represent the heat change or the enthalpy or the heat energy change. You see that this is the heat of the reactant and this is the heat of product. What do you see? The heat of the reactant is higher than the heat of the product. So when you see that the reactant or heat of reactant is higher than product, this is exothermic reaction, which means the reactants are hotter. So from here, you see that the reactants at the bottom, then they try to combine. All these are the stages the reactant has to pass through to get to the product. From here to here is a barrier that every reactant must overcome for reaction to occur or for reaction to be spontaneous. Here to here is the activation energy. Activation energy. Activation energy is the minimum barrier or minimum energy reactants must possess for product to be formed, and it is represented as the EA. And the activated complex is the highest, is the peak of the activation energy. So some reactions don't occur because they don't have the activation energy. What happens? That is the reason for catalyst. Catalyst, they help to speed up or reduce the rate of reaction. What catalyst does is that since this activation energy is so high, catalyst can drop it to like here so that reaction can take place. So if I ask you, how do catalysts increase the rate of reaction? They do so by reducing the activation energy. All that being said and done, let's look at the 3 factors or conditions for spontaneity of reaction. A reaction will only be spontaneous if 1, delta G is equals negative. Delta G must be negative for a reaction to be spontaneous. If delta G must be negative, delta H must also be negative, because delta G is equals delta H minus temperature times change in delta S. This is the formula for delta G, or the relationship between delta G, Gibbs free energy, enthalpy change, and entropy change. 2, for reaction to be spontaneous, delta S must be greater than 0, which means the entropy change must be positive. There should be a high level of disorderliness. 3, for a reaction to be spontaneous, delta H must be lesser than 0. Lesser than 0 simply means negative. So these are the three conditions for spontaneous reaction. Delta G must be negative, delta S must be greater than 0, delta H must be lesser than 0. That means negative. What happens when delta G is equal to 0? When delta G is equal to 0, the reaction is said to be at equilibrium. And when delta G is 0, it simply means that delta H is equals T changing delta S. This is the condition for delta G to be 0. So for equilibrium, delta G must be 0, delta H must be T times change in delta S. And you may be wondering, when is a reaction said to be equilibrium, or what is equilibrium? We will see that shortly under chemical equilibrium. Now let's look at other things that are important when it comes to energy changes or heat changes. The first is standard conditions for measuring heat change. To measure heat change, we have 3 standard conditions. The first one is that 1 mole of substance is involved. 2, temperature must be 25 degrees Celsius or 298 Kelvin. To convert from degrees Celsius to Kelvin, we add 273. 25 degrees Celsius plus 273, that is 298 Kelvin. Then we need 760 millimeter pressure of gases. This is a Jamb pass question. Standard heat of formation is the amount of heat absorbed or evolved. If the heat is absorbed, then we are talking about endothermic reaction. If the heat is evolved, we are talking about exothermic reaction. So the amount of heat absorbed or evolved when 1 mole of a compound is formed from its constituent elements is referred to as standard heat of formation. If elements combine to form compound, that heat that is given up or absorbed for the reaction is standard heat of formation. Now we have the standard heat of neutralization, delta Hn theta. Standard heat of neutralization is the heat evolved, which means it is always exothermic. Heat evolved when 1 mole of water is formed from an acid-base reaction in aqueous medium under standard conditions. And these are the standard conditions. 1 mole of a substance is involved, temperature is 25 degrees Celsius, and 760 millimeter mercury pressure is involved. Then we have the standard heat of combustion, delta Hc theta. Standard heat of combustion is the heat liberated, which means it is also exothermic. When 1 mole of a substance is burnt completely in excess oxygen under standard conditions. When 1 mole of a substance is burnt completely in oxygen under standard condition, that heat is standard heat of combustion. Combustion refers to burning. We have standard heat of solution, delta Hs theta. If you can't see the board clearly, increase your video resolution. This video is recorded up to 1080p, and from my editing, proofreading, and I see that the board is very clear. I go through everything 2-3 times before uploading. So, standard heat of solution is the heat change that follows the dissolution of 1 mole of a substance in so much water that further dilution results in detectable heat change. The standard heat of solution is the heat change that follows the dissolution of 1 mole of a substance in so much water, so that further dilution will result in heat change. And there are factors that affect the standard heat of solution. They are the lattice energy and hydration energy. Lattice energy is the energy used to split up ions in crystal to free them. So split up the ions in crystal so that they become free. That is lattice energy. Hydration energy is the energy released when the free ions are hydrated. And take note that 1 calorie is 4.2 joules. The reason I am not taking much time to analyze all these is that questions come exactly like this. Though you will be asked, the heat change that follows the dissolution of 1 mole of a substance in so much water is dash. Or the energy used to split up the ions in crystal to free them is dash. Like they come exactly like this. So just know them. And this takes us to thermodynamics. You can't talk about heat change or energy without looking at thermodynamics. There are 4 laws of thermodynamics. The first law is the zeroth law, zero th. The zeroth law states that if 2 systems are in thermal equilibrium with a third, they are also in thermal equilibrium with each other. This is the illustration. If we have system A, system B, and system C, this is the third system. If this system is in equilibrium with A is in equilibrium with C, and B is in equilibrium with C, it means that A and B are in equilibrium. You will see equilibrium of reactions very soon, chemical equilibrium. But look at it this way. If this is John, and this is Joy, and this is Jane, if you say that John looks like Jane, the next day you say that Joy looks like Jane, it simply means that if you conclude that John looks like Joy, you are very correct. This is deductive reasoning. If this, then this. From the premises, you arrive at conclusion. And the first law of thermodynamics is the law of conservation of energy. It says that energy can neither be created nor destroyed, although it can change from one form to another. That is the first law of thermodynamics. And the second law of thermodynamics states that spontaneous processes move in the direction of increasing entropy. So as the degree of the suddenness is increasing, as entropy is increasing, the more the spontaneity of the reaction. While the third law states that the entropy of a perfectly crystalline substance is 0 at absolute 0 temperature. For a perfectly crystalline substance, the entropy is 0, which means there is no disorderliness, there is no degree of randomness. The particles are not moving up and down. And at absolute 0 temperature, absolute 0 temperature is minus 273 Kelvin or 0 degrees Celsius. Is the lowest temperature theoretically possible, in fact practically possible. Yes. Delta S is positive in the dash dash process. If you look at all the options, look at water changing from liquid to gas. Delta S positive means there is a degree of randomness of the system. So look at the entropy of the reactant, liquid. Product is gas. So from liquid to gas, the entropy is therefore increasing. So there is a change in entropy in option B, liquid to gas. Gas has a level of randomness or disorderliness than liquid. For the other options, gas to gas, solid to aqueous or solid to solid, gas to gas, liquid to gas will definitely have the highest level of entropy. So option B is the correct option. In the graph above, the activation energy of the catalyzed reaction is that. You see a graph, we have 2 activation energy. One is higher and the other is lower. The catalyzed reaction is the one that is lower because catalyst act to reduce activation energy. That is the function of catalyst. So the one that is lower, look at it. It ends at 200. And where did it start from? It started from 100 and ended at 200. It did not start from 0. Since it started at 100 and ended at 200, therefore, the activation energy is 200 minus 100. That is 100 kilojoule. How about for the uncatalyzed, for the reaction that was not catalyzed? That is the one with the higher activation energy. The activation energy for the higher one, if we were asked, would simply be, it started from 100 and it ended around close to 300. So 300 minus 100, that is about 200. That will be the activation energy for the uncatalyzed. But for the catalyzed, the activation energy is 100 kilojoule, as seen in option C. Ethanol reacts with oxygen to give us carbon dioxide and water. 1 mole of C2H5OH reacts with 3 moles of O2 to give us 2 moles of CO2 and 3 moles of H2O. In the reaction above, the standard heat of formation of C2H5OH, CO2, and H2O are minus 277 kilojoule per mole, minus 393 kilojoule per mole, and minus 286 kilojoule per mole, respectively. Which means for C2H5OH, the standard heat of formation is this. For CO2, it is this. And for H2O, it is this. Why did they not give us the standard heat of formation for oxygen? This is because for elements in their free state, the standard heat of formation is 0. If you have hydrogen gas, it is 0. Enthalpy change is 0. If you have oxygen gas, 0. So any element standing alone, most times or all the time, the standard heat of formation or the heat change or the energy change is taken as 0. In other words, if in this type of question there is a particular element or the one that they don't give you the standard heat of formation, take it to be 0. We are looking for the heat change of the reaction. Now, heat change, delta H, is definitely the heat of product minus the heat of reactant. The heat we are dealing with in this case is the heat of formation, delta HF theta. So this will simply be the same thing. The summation of the heat of product minus the summation of the heat of reactant. Do you know why? We have more than one reactant and we have more than one product. So what next? We simply substitute. For the product, we have 2CO2. 2CO2. So 2 times CO2 is minus 393. Minus 393. Since we have 2 CO2, we multiply by 2. We are dealing with formation plus the second product is H2O, but you have 3 H2O. So 3 times formation of H2O minus 286. Minus 286. So that is it for the product. If we had more than 2 products, we simply add the heat, standard heat of formation of each of the products. So minus that of the reactant. For the reactant, we have C2H5OH, just 1 mole. So minus 1 times standard heat of formation of this guy is minus 277 plus oxygen. We have how many moles of oxygen? 3 moles of oxygen, but the standard heat of formation is 0. So that is how to answer questions like this. Basically, if solved correctly, you should get minus 1367 kilojoule per mole. They are very, very simple questions. From here, food is ready. Remember, delta H is equal summation of heat of products minus summation of heat of reactants. So for the product, we have 1 mole of CO2. No need to multiply by anything. And CO2 is minus 394. For the product, we have hydrogen gas. For a free element, I told you that the heat change or the standard heat change is 0. So plus 0. So we are done for the product. Minus, for the reactants, we have CO. And CO is what? Minus 110. So minus 110 plus H2O. For H2O here is minus 242. Minus 242. So if solved correctly, this will give you minus 42 kilojoule per mole. And the chemical reaction with entropy change of delta S is equals 20 joule per Kelvin, and free energy delta G is equals plus 5500 joule, occurred at minus 23 degrees Celsius. Calculate, temperature is equals minus 23 degrees Celsius. Temperature must always be in Kelvin. That is the standard condition. So plus 273. Calculate the enthalpy. Delta H is equals question. That is the task before us. From spontaneity of chemical reaction, we know that delta G is equals delta H minus T delta S. We don't solve in degrees Celsius, so we convert to Kelvin. How do we do that? We add 273. Take note, the temperature is minus 23 degrees Celsius, not 23. And to convert to Kelvin, you add 273. So you are therefore having minus 23 degrees Celsius plus 273, not 23 plus 273. So minus 23 plus 273 should give you 250 Kelvin. Now, delta S is in joules and delta G is in joules. Normally, we would have solved in kilojoule. Since the units are the same and the answer is in joules, why should we convert? So we solve in joules. And solving simply involves substitution. So here you have delta G 55,000 is equals delta H minus temperature 250. 250 times 20. Yes, 250 times 20. So 55,000 is equals delta H plus 5,000. Delta H minus 5,000 rather. Delta H is therefore 55,000 plus 5,000. That will simply give you 60,000 joules. Ladies and gentlemen, that is it for spontaneity of reaction. This brings us to the end of this class. Please install the Flashlearners Jamb app and begin to play with questions. If you have issues, complaint, inquiry, or you need advice, someone to talk to, mentorship talk, feel free to reach me via my social handles. Ladies and gentlemen, see you in the next episode.